Australia's next top flood zone. With sea levels dominated by the day-to-day tides, Newcastle, New South Wales is a proven performer where coastal flooding is regular and predictable. Our second contestant is Perth, Western Australia. Extreme sea levels here are caused by storms, so flooding doesn't happen that often, but when it does, it really puts on a show. Our third contestant is the Gold Coast. With its low-lying position sitting close to the water, it doesn't take much for it to flood. Our final contestant is notable for its small differences between high and low tides. This makes it very vulnerable to even modest amounts of sea level rise, so Melbourne has a lot of potential to challenge for the title in the years to come. Which city or town will become Australia's next top flood zone? Join me on my PhD journey to find out.
Hi everyone, my name is Ben Hague. That was a video I made for Monash's Visualise Your Thesis competition about my Bureau of Meteorology and PhD work. I'd like to start by acknowledging that I'm giving this presentation from the lands of the Wurundjeri people of the Kulin Nation and pay my respects to their elders, past and present. Today, I plan to talk about how we are conducting our search for Australia's next top coastal flood zone, the progress we've made thus far, and some of the things we've found along the way. This talk will mainly draw material from two recent papers, which are shown here, and I can put the links in the chat at the end of the talk. The starting point for my talk today is how we are defining sea level extremes by their consequences rather than their likelihood. And through the example of Sydney, Australia, this will lead to a discussion of how this impact-based framework can be used to investigate the changing nature and predictability of coastal floods. I will then demonstrate what we mean by, I will then demonstrate the term emergence times and discuss this as a new coastal risk assessment metric that gives insights into the frequency of future coastal flood impacts. So firstly, currently standard practice in research and industry is to define extremes by their likelihood, rather using such metrics as sea level allowances, amplification factors, and return periods. And there's some examples of these here from Sydney. And you can see that, so the sea level allowance, for those who are unfamiliar, is the vertical distance that an asset needs to be raised under rising sea levels, so the projected sea level increase doesn't change the risk. And amplification factors is, and then the amplification factor is looking at an event that occurs at a specific frequency at the moment, and how many more times often that event will happen in the future. However, there's some circumstances that don't really lend themselves to these sort of analyses. And these are questions like, when will an event like this happen, say 10 times a year or weekly? And how sure can we be of when this event will occur in terms of time of day or time of year? This talk sets up the science needed to answer questions such as these. So we can define extreme sea levels by their impacts rather than by their likelihood. And we do this by defining coastal inundation as occurring when still water levels are sufficiently high to flood coastal assets like streets, paths, jetties, gardens, and buildings. And there's a number of factors that contribute to still water levels being this high. The largest contributor of the day-to-day variability of sea levels are the astronomical tides. And these arise due to the gravity of the Earth, Sun, Moon system. And these are very predictable, with tide tables produced years in advance by the Bureau and other agencies around Australia. There's also a number of factors that are predictable at much shorter lead times. And one of these is storm surges, which come from low pressures and strong winds from cold fronts, tropical cyclones, east coast lows, and other weather systems. There's also coastal trapped waves, which propagate areas of high sea level along the coast away from these storms. And you can see in this animation here that there's a cold front that approaches South Australia, causes a storm surge, but then you actually see that there's a wave that propagates along the coast with some high sea level anomalies reaching the northern New South Wales coast. And these sort of events have been documented to coincide with a number of past coastal inundation events, particularly along the New South Wales coast. Climate variability such as El Nino and La Nina can also cause sea levels to differ from what is predicted in the tide tables, with predictability on monthly timescales. And again, you can see here the changes in sea surface height during a La Nina and El Nino events over time. Mean sea level changes are important too, because as sea levels have risen, the vertical distances between the highest tide of the year and the flood level has decreased. And this vertical distance is called freeboard. So that's the difference between the highest, between the height of the tide and the impact-based threshold. So in some places where you used to need a storm surge to exceed the flood threshold, you can now exceed the threshold by tides alone. And this is where this negative freeboard situation occurs. Hang on, I don't think I've got my pointer on. Here we go. And then you've got this situation where there's negative freeboard, and this is where tides can occur. Flooding can occur due to tides alone. And we call this tide-only inundation, and we'll discuss this a bit more later on. So what does coastal inundation look like? Well, it can be water spilling out of a watercourse onto infrastructure, such as in this example from the tidal Swan River estuary in Perth. Or it can be forced up stormwater drains, such as in this example from Bobbin Head in Ku-ring-gai National Park, just north of Sydney. And it can also happen through groundwater intrusion, although I haven't found a lot of reports of this happening in Australia, but that doesn't mean to say that it doesn't exist. What we're not talking about is things like coastal erosion and wave overtopping, as we're focusing on still water levels rather than total water levels. And we're really only looking at what can be measured by tide gauges. But this is some future work that I'm hoping to look at some stage as well. And so the degree to which high sea levels cause impacts has a lot to do with other environmental and human factors unrelated to the drivers of day-to-day variations in coastal sea levels. And these factors are also important in determining the vulnerability of certain locations to more frequent or more severe impacts as sea levels rise. One of the key factors is tidal range, which is the difference between the high and low tide, as you can see in this diagram here. Tidal range varies around Australia from around 1 metre to around 10 metres, but in the New South Wales region, it's reasonably constant at around the 2 metre mark. A small tidal range means that the impacts of sea level rise are felt more quickly for the given amount of sea level rise. So you can see here 80 units of sea level rise, you go from the impact-based threshold being just above the highest tide of the year to being close to mean sea level. Whereas in this case, with 80 centimetres of sea level rise, you see it starts just above HAT, but the impact-based threshold ends up halfway between mean sea level and HAT. So you end up with this situation in this bottom plot where you'll get much more frequent flooding and also longer duration when flooding happens. Whereas in this top scenario, you'll get less frequent flooding and it won't happen for as long on average. And this is just due to the tidal range. There's also, so the frequency of storms and storm surges is also important, in particular in sort of the nature of the risk. And you can see examples here that in Newcastle, for example, most of the still water level is made up by the tides, and there's occasionally some storm surges, but they're not usually that large. But when you compare to Perth, is that you actually have quite regular storm surges that are quite large. So this affects the coastal risk, and particularly as sea levels rise, it means that you can go, in the case of Newcastle, from a regime that's primarily storm surge dominated to a regime that's mainly tide dominated very quickly, whereas that takes longer if you get more frequent storms in places like Perth and Melbourne. And the orange is the tide and the blue is the total water level. So the storm surge is basically the blue bit you can see. Flood mitigation works can also affect flood risk, as does the elevation of assets and where townships are located relative to water. So for example, whether they're on a cliff, like in this example, or whether they're sort of on an estuary or a river. Planning decisions can also affect coastal risk, and particularly if things like land buybacks occur, which is the case in Windsor. In Brisbane, this will mean that sort of the assets that flood when you get high water levels will change, and that may mean that it's not as much of a concern to people. And it's because of these environmental and human factors that we cannot simply use a statistical parameter such as the highest tide of the year or the 1 in 100 year extreme sea level height, to accurately assess the risk of coastal inundation at a specific location. And that's sort of the starting point for the work that we've done in Sydney. So Australia doesn't have official coastal flood levels for coastal flooding in the same way that we do for riverine flooding. So we've developed a method to define such thresholds. And the way that we've done this is we've matched reports of coastal impacts to water levels at nearby tide gauges. So for Sydney, you can see here there's a number of different tide gauges in blue and the observations are in red. And this is a collection of impacts that we use to define our flood thresholds for Sydney for this study. We found that Fort Denison was representative of all of the gauges in that the correlations between them were high, and the sort of when events recorded high sea levels and when they didn't was also well correlated between the different sites. So we've just used Fort Denison as representative of the broader Sydney region. And when we look at the table of impacts, we can see that generally that these events where Fort Denison reaches certain levels, you see flooding in a number of different locations around Sydney, and you also see flooding happening in the same locations over multiple events. So for example, Botany has flooded there's a few impact reports on Botany on this list. And we defined 3 different flood levels. We defined low impact flooding, minor flooding, and moderate flooding. And these are with respect to the tide gauge 0 at Fort Denison, but you could convert them to AHD if that was what you wanted to do. So minor flooding and moderate flooding, the impacts associated with those are defined so as they're consistent with the minor and moderate flood warnings issued for riverine flooding by the Bureau. And low impact flooding has been defined to encompass some more nuisance style impacts, such as jetties and boat ramps flooding, and partial covering of paths rather than complete submergence. You'll notice in this table that there's quite a lot of impact reports that have been sourced from social media, and Witness King Tides is also a social media source. And the reason that we've done this is because this study, I guess, is sort of exemplified by this study, which is that they found that a number of large populations that might be currently exposed to flooding couldn't be identified as being exposed to flooding using standard measures. So in other words, if you're wanting to forecast impacts and study impacts, you really need data on the impacts. They also discuss the concept of remarkability, which was essentially the concept that if somebody posts on social media or a newspaper reports about flooding, then it was obviously of interest to the people and potentially of concern. So if you don't have a framework like we do for riverine flooding that you could adapt to the coastal space, or you're interested in a metric that was sort of independent of that, you could look at this idea of, well, if people have posted, then obviously there was a reason that they did it, and then maybe that's the level of concern, and maybe that's where you should be looking to as sort of setting a threshold for looking at coastal flooding that is concerning to people. So in Sydney, we've defined these three thresholds as I discussed earlier, and we can look at the exceedances of these thresholds as a proxy for the frequency of coastal flood events in the past and in the future. And one of the benefits of this for Sydney is that we have a 100-year-long tide gauge record from Fort Denison, so we can use these thresholds to derive estimates of coastal flood frequency through time. We can look at, so low impact flooding is in the pale blue, minor flooding is in this medium blue, and moderate flooding is in this dark blue. And again, they're overlaid on each other. So low impact flooding has increased from around 12 days a year to around 23 days a year over this period. Minor flooding has increased from about 1.6 days per year to around 8 days per year. And moderate flooding has gone from occurring once or twice in the first 50 years to occurring every few years in the most recent 50. One of the questions that we wanted to ask in our research was what is causing this increase in frequency of coastal floods? And this is what the focus of the second part of my talk will be. And there's also an interrelated question here, which is, are floods becoming more predictable? And how can we use that? And how can we investigate that change? So plotted on this plot when it comes up is the same as what we had before, except instead of looking at coastal inundation, we're looking at tide-only inundation. So this is looking at the number of times per year that the highest tide of the day has exceeded the impact-based thresholds in each year. And we can see that for low impact levels, which is this pale blue, that it happened about 3 times. It's happened 3 times per year in the first 20 years, and it's happened about 13 days per year in the last 20 years. And we found that 19% of all minor coastal inundation days in recent years, so that's of the two slides back, that 19% of them would have occurred due to tides alone, regardless of the weather conditions, despite the fact that this tide-only minor flooding never occurred prior to 1991. So what is this tide-only inundation and how have I defined it? Well, it turned out that looking at what the tides were was not as straightforward as we first thought. And it comes down to the fact that you have to work out what you're going to say was the part of the tide prediction and what was part of the residual after the fact. I mean, you could, if you had archived tide predictions, you could use those, but we don't have archived tide predictions going back to 1914. So you have to derive a tidal analysis going back in time. And to do this, you need to make choices as to what you're going to include in part of the tide prediction and what you're going to include as part of the residual. And this choice isn't trivial. We looked at a number of different methods to do this. And one method, so our method estimated 13.4 days per year over the recent period. But other methods estimated 10 and another one estimated 23. So it shows that there's definitely some sensitivity to how you choose to do this analysis. And in some respects, that's okay, but you need to be aware of it. And sort of, I guess that's sort of why I wanted to spend a little bit of time justifying why we've done what we've done. So we've used this partitioning and we used a global mean sea level reconstruction to specify the long-term changes in mean sea level. And we put the long-term changes in mean sea level, the mean sea level, which is the datum offset between the tide gauge 0 and whatever other metric you want to use, the harmonic tides, and they all went into the tide predictions, which these are all sort of things that you can specify or you have reasonable confidence looking at over a long period of, say, decades to centuries. The things that were left in the residuals were things like interannual mean sea level variability. So this is things like ENSO, changes in currents, those sort of things, and also short-lived sea level anomalies. So they both ended up in the residuals. And I won't go into great detail of why we arrived at this, but maybe it's something we can chat more about in the questions if people have questions about it. I will mention briefly, though, that we used the global mean sea level reconstruction rather than the observed trend at the location, because the observed trend includes this interannual mean sea level variability. And we didn't want to do that because if you look at the future projections, they don't include things like ENSO and changes in currents. They just include the rise in sea level due to melting of ice caps and glaciers and thermal expansion and those sort of things. So we wanted to try and define it in a way that could be applied consistently from the past into the future. Now, I also want to point out that tide-only inundation is not a subset of coastal inundation. They are sort of distinct phenomenon, although we actually argue that tide-only inundation isn't a physical phenomenon for that reason. We more say that it's a metric to look at the effects that tide and sea level rise are having on coastal inundation. So you can have this case here, which is where you have the predicted tide exceeding the flood threshold, but you get a negative residual on the day, and that means that the observed sea level doesn't actually exceed the threshold. There's also cases where you can have coastal inundation, but not tide-only inundation, which I guess is sort of this traditional event before we had sea level rise, where you needed to have a storm surge on top of a high tide to cause flooding. And then there's also this case where both of them happen, which as we've seen is happening increasingly often, that both of these are occurring simultaneously. Which means that really it isn't sort of two separate circles. They're actually circles that are joined together. But we know that in the 20-year period to 2015, that tide-only inundation occurred at approximately 2/3 of the rate of coastal inundation. And this was a much larger rate than it was 100 years ago when it was 1.4%. Basically, inundation was almost impossible without something elevating tides above the predicted tide level. However, as I mentioned earlier, in reality, these two occurrences are not mutually exclusive, and there's overlap between the circles, such as there is here. As sea level rise continues, we expect that both circles will grow in size, with the size difference between the two circles getting smaller and the overlapping area getting larger in the future. And this represents the fact that tides will play a comparatively greater and greater role in future coastal flooding, with flooding happening more and more often. And this goes back to this concept of freeboard that we discussed at the start, which is that as sea level rises, the distance between the highest tides and the impact-based thresholds decrease. And then as sea level continues to rise, more and more tides exceed the impact-based threshold. So there's fewer opportunities for a storm surge to be the difference between exceeding the threshold or not. And of course, this doesn't mean that storm surges aren't important in the future. They will just be the difference of whether you exceed the threshold by a lot or whether you say have moderate flooding rather than minor flooding, rather than actually being the difference of whether minor flooding will happen or not. So we can do projections of coastal flooding frequencies using sort of adapting this method that we've already described for historical flooding. And we've assumed here that the minor flood threshold stays the same through time. So that basically we're looking at the present day flood risk and then looking at that, the present day exposure, and then looking at that in the past and in the future. So we assume that sea levels of 2.06 meters will always cause minor flooding. And that may not be the case if there's flood mitigation works and the like, or it may not have always been the case in the past because the assets that get flooded to trigger the minor flood threshold being reached weren't there 100 years ago. But under these assumptions, we can see that minor flooding occurs approximately weekly by 2050 and daily by 2100, and moderate flooding occurs around 20 days a year by 2050 and around 350 days per year by 2100. And I'll briefly explain what's on these plots and then sort of demonstrate why this is sort of a key finding of ours. So in the black, we have observed tide-only inundation. We have tide-only inundation in black. The observed is in the black solid line. And then the dashed and dotted lines are the future projections. And I'll show on the next slide how we derive those. And then in blue, we have the observed coastal inundation, which is, so this is the observed, the observations, the still water level observations exceeding the impact-based threshold, whereas this is the predicted tides exceeding the impact-based threshold. And then we have the projections of coastal inundation with the 5th percentile and 95th percentile following the IPCC reports, and then the median estimate is there. And one of the things that you notice that happens in the second half of the century and potentially even before with minor inundation is that there's convergence between the blue lines and the black lines. And this represents the fact that tide-only inundation will occur at the same frequency as coastal inundation in the future. Now for Sydney, where there's generally reasonably small storm surges, this means that pretty much all the flooding happens when there's high tides. So this is how we derive the different methods, and we derive them using independent methods for reasons that will become apparent in a minute. So for tides, what we did is we derived harmonic tides based on harmonic constituents derived over a 20-year period, and then we were able to produce predictions based on that going back, and then predictions going forward, or analyses rather than predictions, I guess, because we're sort of doing them in retrospect. And then we use the IPCC mean sea level projections as the mean sea level about which the tides rise and fall in each year. So it's basically this situation where you have the predefined tides and you just increase them higher and higher as sea levels rise in accordance with the projections. Conversely, for coastal inundation, so this was for looking at the still water level exceeding the impact-based threshold rather than the tides exceeding the impact-based threshold. We looked at a 20-year period of climatology of the number of days per year where, or the highest sea level recorded on each day. And then we shifted that distribution to the right by the however many centimeters the projection for that year was. And then we've taken an average of the 20-year period as the estimate for each year. And as you can see in these schematics, that we've assumed that the storm surge characteristics stay the same, so that the storm surges don't become more severe or more frequent. And we've also assumed that the tidal constituents stay the same. Now, this may not be the case, but you could also, and this is something we may look at in future work, you could also look at a case of, well, if variance increases by 10%, what happens? If tidal range increases by 10%, what happens? We also tested deriving the tide-only inundation estimates using this shifting method for coastal inundation, and we found that the results were very similar, which sort of provided us with some confidence that this method was reasonable to use. And the reason you want to use this method for tide-only inundation is because you can get this jagged sawtooth pattern, which represents the nodal cycles. And these are very important for predictability because it shows that some years are more prone to coastal flooding than others based on the tidal properties of the location. And we've also looked at different emission scenarios, and we can also look at ARIs in the same framework, is that you just look at whatever the ARI is from whatever source you want to use. We took these from a New South Wales state government report on sort of coastal hazards. And you can just look at, well, how often does that level get exceeded in the future in the same way that we've done for the minor and the moderate flood thresholds. And you can see that different emission scenarios result in quite different futures. Although you still end up with events that were once very rare occurring multiple times per year. And I've sort of described this as that the future emissions will determine whether multiple times per year is in the order of tens or hundreds of days per year. And that depends on whether you follow a low emission scenario like RCP 2.6, a moderate emission scenario like RCP 4.5, or a high emission scenario like RCP 8.5. And all of the results to date have shown RCP 8.5. This also shows some of the, I guess, communication difficulties in talking about a 1 in 100 year event with the public. And of course, we know that a 1 in 100 year event will happen more than once every 100 years, either because of randomness or because that there's a trend in the data series. But using this method, we can actually estimate that the 1 in 100 year event will happen around 3,600 times under RCP 8.5, to the point where it's happening most days of the year by 2100. And of course, it's happening. That's in the high scenario. In the lower scenarios, it's not happening as frequently, but it is still happening multiple times per year in all of those scenarios. And most of these 3,600 are in sort of the last 20 years of this century. So it's this high frequency of coastal flooding that is why I parenthesize the word coastal in my title slide, because coastal flooding isn't the biggest player in the broader flood space currently, but it may well be by the end of the century, at least judging by these results for Sydney, because I don't foresee a future where pluvial or riverine flooding will happen multiple times a week. But this is the scenario facing us in the coastal space, at least in Sydney. And our future work will look at determining to what extent this is also true for other locations around Australia. And I'll talk a little bit more about that when I discuss the future work at the end of this talk. So the last sort of highlight of my search, I guess, that I want to talk about today is what we are terming, which is what we are calling emergence times. And this helps answer questions like when will an event like this happen every year, 10 times a year, or weekly or daily? And there's a scenario that where this sort of information could be useful to somebody who owns a property by the water, or their mortgage lender, or their insurance company. And our framework allows you to sort of have a go at answering these questions. So we developed the concept of emergence times to assist planning decisions, and we define an emergence time as basically by which year a certain frequency of coastal flooding will occur under a certain sea level rise scenario. And this is pretty flexible. You could choose whatever number you like. 30 days per year has been shown to be sort of a key threshold for when flooding becomes chronic in some studies in the US. But you could also look at RCP 8.5 or RCP 2.6, or you could define your own scenario depending on the local conditions or whatever planning requirements there are. So in this example from this cafe that's in Tea Gardens, just north of Newcastle, we will assume for the purpose of this exercise that the moderate flood level in Sydney is a reasonable threshold to use for this analysis. And we know that the water levels in Tea Gardens and Sydney are pretty similar. So for the purposes of this example, we think this sort of will illustrate reasonably well the sort of things we think we can do with this emergence time method. But going back to, well, what sort of answer could you give the people based on the sea level allowances? And you're really restricted to statements along the lines of, well, in order to keep the risk constant in 2050, you need to have the building about 30 centimeters higher than it was in 1986 to 2005. And this is useful information if they're wanting to raise the building. However, they may not be able to do that, or it might be impractical, or it may be too costly. So asking the question of how often will it occur if you don't do anything can also be valid in some of these sort of situations. And that's what this emergence time idea gets at. So what results do we find? Well, for the moderate flood level in Sydney, this is as simple as taking the horizontal slices of this plot that I showed before. And we find that if you take a horizontal slice at 30 years, that you find that by 2054, under RCP 8.5, you'll see flooding around 30 days per year. If you're interested in weekly flooding, 2062, and then there's and then with the 90% confidence interval that the that the IPCC place on their RCP projections, you can see there's sort of about 10 years either side, depending on whether we're on the high side of 8.5 or the low side of 8.5. Similarly, you could also look at, well, what do you have if there's a lower emission scenario like RCP 4.5 or RCP 2.6? You can also look at, well, okay, what happens if you can do some flood mitigation works that mean that your threshold for flooding is no longer 2.2 meters, which is the moderate inundation threshold, but it's now 2.4 meters. And 2.4 meters is coincidentally the highest on record observation for Sydney. And this is effectively pushing this plot to the right by 20 centimeters. And what you see is that this extra 20 centimeters buys you about 21 years of time so that it reaches this 30-year threshold 21 years later than it would have otherwise if you didn't sort of do this mitigation work, for example. You can also see here that in general, the lower emissions scenario for the amount give you more bang for your buck, as do these lower thresholds, so that you can buy more time for your amount of sea level, for the amount of change you can have to your threshold. And now all of these values, this 20 centimeters, 20 years thing, I don't expect will be something that will be true for other places in Australia. This is going to be very localized and very much dependent on factors like tidal range, on storm frequency, and on where the threshold, where the impact-based threshold sits relative to the highest tide of the year. But nevertheless, you could do analysis like this for other locations in Australia. And you can also look at, I've picked 2049 because that's the peak of the nodal cycle around 2050. You can also look at, well, there's 21 days where we expect that the tide will exceed this threshold of 2.2 meters, and these are listed here. And there's a few interesting things that you can find from this. And one is that a lot of these flood events are going to happen during winter evenings. And there's a smaller number that will happen during summer mornings. And these are times of the full moon and the times when the gravitational potential for the tides is the largest. And this could be useful if the actions that were needing to be taken to mitigate the risk changed from daytime to nighttime. And that could help people make decisions as well, giving some idea of when is the most likely time that flooding will occur. Now, of course, there could be a storm surge in March that coincides with the highest tide in March, but it's a really big storm surge, so you'll also exceed it. So it's not going to cover all scenarios, but it gives you this idea of, and this level of detail that other methods don't give you. So that's sort of the three main things that I've wanted to cover today. I'm going to briefly talk about what some of the next steps are. So as Anna mentioned in the intro, we're working on a high quality tide gauge data set. We're also looking to combine that data set with further reports of impacts from around Australia, which we're currently gathering. If anybody has any that they would be interested in contributing, I'd be very much interested in talking to you about it. And then that will sort of allow us to define coastal flood thresholds for other places around Australia in a similar way to what we've already done for Sydney. It will also allow us to do a national assessment of present, past, and future coastal flood risk, and looking at things like, well, does tidal range have the same role in all the different places, or will some places become tidal much quicker than others, and some of those things that seem reasonably logical extensions to the analysis we've done so far. And there's a few other projects that are in the works as well. There's characterising the oceanographic conditions that lead to impacts on open coasts in Victoria, and this is work that we're doing with Chloe Leach at the University of Melbourne. And also Pacific sea level trends and impacts is some other work that we're looking at doing at the Bureau. So overall, I hope that this work means that our next steps towards an improved understanding of Australia's coastal flood risk are not like this guy's next steps. Thank you.
Thanks a lot, Ben. Really fascinating talk. We've got time, we've got about 15 minutes for questions. So if anyone wants to ask a question, feel free to turn on your microphone.